Let's look at some examples using the chain rule. For example, if y is equal to log e x plus cosine x, I see that I have something in parentheses. I'm going to say let u equal x plus cosine x. I know I have to use the chain rule because I've got something besides just log x. So let u equal x plus cosine x. Therefore, du dx, I take the differentiation of u with respect to x, because I have u's equal to x's there, is equal to 1 minus sine x. And you can see how important it is to know this by heart so this doesn't trip us up. Well then, write this as y is equal to log e, which is the same as natural log of u. Well, I need to know what dy du is. Well, dy du is going to be 1 over u. Now I can finally use my chain rule. Dy dx is equal to dy du times du dx. So dy dx is equal to, well, dy du is 1 over, it's not just u, we know u is equal to x plus cosine x times the derivative of du dx is 1 minus sine x. So my final answer is, I can multiply that by 1 minus sine x over x plus cosine x. At this point, I'd always be trying to simplify that, but that's as far as we can go there. Let's do another example of differentiating using the chain rule. For example, if I have y is equal to the square root of 1 plus sine squared x, I have to recognize that I can write this as 1 plus sine squared x to the 1/2. And I can treat 1 plus sine squared x as the u. So for example, if I'm going to find dy dx, I have to treat this as the u. So if that's u, then my differentiation process will be 1/2, I bring that out front, times, that is my u, minus 1, so 1/2 minus 2 over 2 is negative 1/2, times the derivative of this, which will be my du dx, which will be, bring the 2 out front, 2 sine x, and then what's the derivative of sine x? Cosine x. So I had to use the chain rule twice there, because if I'm considering the derivative of sine squared x, what's sine x squared? Which I had to bring the 2 out front and then take the derivative of sine x, which is, of course, cosine x. 2 goes out front and 2 goes to 1. That's where I found the derivative of this. Well, if this is u, I don't need to actually go to the u's. This is how I do it in my private math life, like that. Now I can consider, what does this really mean? Well, this is 1/2, so the 2 stays down below. This is to the negative 1/2, which means I'm going to put this here, 1 plus sine squared x to the 1/2. This negative just means I'm in the wrong place. If I'm in the numerator, bring me down below. And this stays multiplying by the 1 in the numerator. 2 sine x cosine x. Of course, because we have multiplication here, the 2's can cancel. Only when we have multiplication do we cancel those 2's. We have sine x cosine x divided by 1 plus sine squared x, and this is all to the 1/2, or to the square root. Let's do some relatively easy examples using the chain rule. For example here, y is equal to the square root of 2x cubed plus 1. First, you have to recognize you could write this as 2x cubed plus 1 to the 1/2. And now this parentheses with more than just x in it tells it you're going to have to use the chain rule. Let u equal to 2x cubed plus 1. So dy dx is equal to dy du, which would be 1/2. Your u is 2x cubed plus 1 to the 1/2 minus 2 over 2, which is negative 1/2, times the derivative of whatever in parentheses would be 6x squared. So this would leave us with 6 divided by 2 is 3x squared times 2x cubed plus 1 to the negative 1/2, which we can simplify to 3x squared over 2x cubed plus 1, and that's in square root. If y is equal to sine squared x, we can write that as y is equal to sine x squared. And of course, now our u becomes sine x. So dy dx becomes 2 times sine x to the 2 minus 1, which is to the 1. Now, what's the derivative of sine? That's cosine x. So we get 2 sine x cosine x as our derivative of this one. And last but not least, if I have y is equal to log e tangent x, I can write that as y is equal to natural log tangent x. And I recognize that my u is tangent x. So what is my derivative, if I could write it down here? Dy dx is equal to, well, I know the derivative of natural log is 1 over. 1 over what? 1 over my u. What's my u? Tangent x. And what's the derivative of tangent x? I now have to write that. This is now my du dx. Tangent x is secant squared x. So I get secant squared x over tangent x. As I said, these are relatively easy examples of using the chain rule. Here is one more example of using the chain rule. And here we have a situation where it's going to be a little more complicated. Why? Because we see we have one function, e to the x cubed. Now that's a complex function. It's not just e to the x, it's e to the x cubed. So we could define e to the x as f of x and x cubed as g of x. Or we could say, well, let u equal x cubed. And it's multiplied by another function. So when you're seeing take the derivative and multiplication, you'd be thinking about the product rule. So this particular problem asks us to use the chain rule in this part, and also this is not just sine x, it's 1 minus 2x. Again, we're going to have to define u as 1 minus 2x in order to do this out. We're going to have to use the product rule and the chain rule. So dy dx will be, I have to think of the product rule. It's the derivative of the first. Well, that's going to be e to the x cubed times 3x squared. I just used the chain rule there. Times sine 1 minus 2x plus the first, e to the x cubed, times the derivative of this. Well, the derivative of this will be cosine 1 minus 2x times the derivative of whatever's in parentheses there, which we call du dx, which would be negative 2. Notice if I'm going to multiply by negative 2, I put it in parentheses there. I don't just put a minus 2 there and maybe get confused later on thinking that I was supposed to subtract that. Well, this certainly is a mess. We can clean this up by factoring out an e to the x cubed, which would leave us with 3x squared sine 1 minus 2x plus, well, plus a negative 2 cosine 1 minus 2x, like that. And we're done.